This tape has two sections. The first is a review of the mysteries of weight and balance by Dr. Jack Wellman. After Dr. Wellman's review, we will present a pilot operating handbook study of the information used by Beech for proper loading of the Bonanza. We'll offer a simple method for constructing a graph for a loading schedule that will enable a Bonanza pilot to decide quickly and easily if the planned loading will be within the envelope. In spite of their phenomenal safety record, Beechcraft airplanes are not strangers to weight and balance problems. At gross loading, there is a narrow range. Sometimes recommendations have been made to carry weights permanently mounted at strategic points. Among potential problems, rearward loading outside the envelope with the attendant light control forces are considered a factor in some Beech structural failures when recovery has been attempted after an upset in turbulence. Bonanza's loaded improperly magnified dangerous spin characteristics should an inadvertent entry into a spin be made. But Beech has made the loading evaluation very easy if one is prepared to spend a little time before flight. This tape will offer a system that will make it even easier and further reduce the time spent.
Time you gave any thought to such phrases as mean aerodynamic chord, datum, arm, limit load. Hello, my name is Jack Wellman. I'm Director of Program Development for Airmanship Incorporated, the knowledge center for today's pilot. And in this presentation, we'll be talking about weight and balance, and we'll be using those terms. As you progress through this presentation on weight and balance, you'll probably have a few moments of confusion and doubt. Remind yourself that others before you had to figure similar problems without the assistance of the FAA to define terms, or the aeronautical engineers to set the limits for you, or airmanship to put it all together in living color. By the time you finish this presentation, you will rediscover the meanings of the following terms: maximum takeoff weight, empty weight, zero fuel weight, basic operating weight, useful load, maximum ramp or taxi weight, center of gravity, fuel load, mean aerodynamic chord, moment index, datum, arm, moment, limit load, and ultimate load. We will review the concepts of aircraft stability, how the center of gravity limits are determined, and the consequences of an out-of-balance aircraft. First, let's deal with weight. Your plane will have designated for it two important weight figures. These are the empty weight and the maximum takeoff weight, sometimes referred to as the maximum gross weight. The empty weight consists of the airframe, engines, and all items of operating equipment that have fixed locations and are permanently installed in the aircraft. It includes optional and special equipment, fixed ballast, hydraulic fluid, fuel and undrainable residual fuel and oil. When oil is used for propeller feathering, it's included. Maximum takeoff weight is the maximum allowable weight at the start of the takeoff run. Some aircraft are approved for loading a greater weight, ramp or taxi weight, only to allow for fuel burn-off during ground operation. The takeoff weight for a particular flight may be limited to a lesser weight when runway length, atmospheric conditions, or other variables are adverse. Useful load is the weight of the pilot, co-pilot, passengers, baggage, and usable fuel. It is the empty weight subtracted from the maximum allowable takeoff weight. Some aircraft which have a high fuel burn rate are allowed to load heavier than the maximum takeoff weight. The difference between the ramp or taxi weight and the maximum takeoff weight is the fuel which the crew estimates that the airplane will burn during taxi and run-up. Other aircraft also have a maximum landing weight listed in their operating manuals. This is the maximum weight at which the aircraft may be normally landed. The maximum landing weight may be limited to a lesser weight when runway length or atmospheric conditions dictate. Within the FAA glossary of terms are two more weight definitions. Basic operating weight is the weight of the aircraft, including the crew, ready for flight, but without payload and fuel. The other term is maximum allowable zero fuel. It is the maximum allowable weight authorized for the aircraft, not including the fuel load. Zero fuel weight for each particular flight is the operating weight plus the payload. These two terms would be most applicable in the charter and freight divisions of general aviation. Among some pilots, there is an erroneous impression that the maximum takeoff weight is the limit that a plane can lift off the ground. While this may be true under certain conditions of density altitude, it is not the basic reason for a maximum takeoff weight. This limit is determined primarily on the basis of the aircraft's structural design. The wing will only support so much weight. As an example, the FAA requires that all aircraft under 4,000 pounds in normal category must have a minimum limit load factor of 3.8 Gs. The limit load is that factor which an aircraft can repeatedly encounter without creating any structural damage. However, the stressing of an aircraft goes far beyond the limit load. Most general aviation aircraft are designed to accept a force 50% greater than the limit load for one occasion without structural failure occurring. This load factor is called the ultimate load. Between the limit load and the ultimate load, structural damage may probably occur in some form, but the aircraft will not come unglued in one single incident. A chart displayed here is commonly referred to as a VN diagram. On the grid, load factors are represented by horizontal lines and indicated airspeed in miles per hour by the vertical lines. The area enclosed by dotted lines is what you might call the operating envelope for the aircraft. Radiating out from 1G on the left margin are lines representing gust forces in feet per second. Note that above the 1G line, these gust forces are positive. These positive and negative gusts are related to the attitude of the airplane. On our diagram, we have used colors to illustrate the relationship of this diagram to your airspeed indicator. Point A is the minimum speed at which 1G can be maintained and is established as the stall speed. Lines C, E, and I, G represent the limit load. Structural damage may occur in any area of the diagram which is shaded gray. Maneuvering speed for this plane is located at point C. The curved portion of the dotted line is essentially a continuation of the level stall speed found at point A. Airspeeds less than that at point C cannot produce loads capable of damaging the aircraft. Well, let's suppose that you flew into some turbulence which called for reduced airspeed. You reduce your speed to 100 miles per hour. Suddenly you're hit by an upgust of 30 feet per second. Look at the chart where the 100 miles per hour and the 30 feet per second gust lines cross. The point is outside the operating envelope, meaning that under those conditions you would stall. Sticking with the maneuvering speed for your aircraft will assure you of not exceeding the limit load while keeping you away from the danger of an inadvertent stall. An aircraft with a maximum takeoff weight of 3,500 pounds will have a limit load of 13,300 pounds based on a factor of 3.8. Now, on a cool day, you could probably get the plane off the ground with a 500-pound overload. However, if you were to hit an upgust, which put a 3.8 G force on your plane, you would be forcing it to accept a full ton more of weight at that instant than it was designed to take. A post-flight inspection should be conducted to locate any wrinkled skin or popped rivets. Repeatedly subjecting your plane to this type of stress may even cause catastrophic failure to occur on some occasion before the ultimate load factor is reached. A negative limit load factor is also designated for all aircraft. It is usually a smaller number except for aerobatic aircraft. Other than down gusts, most aircraft do not receive many really heavy negative G-forces, student landings being the exception, of course. Weight or gravity is one of the four forces acting upon an aircraft in flight. Lift must be greater than weight for an aircraft to get off the ground and fly. The greater the weight, the greater the lift must be to support the plane. If you are forced to produce more lift to support the additional weight, you must also be forced to produce more induced drag. In order to overcome additional drag, you must increase thrust or power. What all this means is that what your airplane weighs on a particular flight will determine to a great degree how much fuel you are going to use. It will affect takeoff performance, cruise, and landing performance. A pilot with an eye towards efficiency will keep his plane as light as possible within the realm of safety. Let us return to a statement we made a few minutes ago concerning maximum takeoff weight. We stated that the maximum takeoff weight was determined by the limit load factor rather than the capability of lifting a certain load off the ground. It is also a fact that there may be atmospheric conditions present which would prevent your plane from getting off the ground even with a load considerably less than the maximum takeoff weight. You know these conditions by the term density altitude. In another tape, we will discuss takeoff performance. But we would like to remind you that conditions of temperature, humidity, altitude, and air pressure must be considered carefully before any takeoff in a fully loaded aircraft. In fact, FAR 91.5 requires that you check all these conditions. It is possible that in several models of general aviation aircraft with all seats filled, baggage at capacity, and full tanks, the maximum takeoff weight may be exceeded. One reason for this is that the FAA has a schedule of standard weights which the aircraft companies use in computing useful loads. The standard weight of a general aviation passenger is given to be 170 pounds. Well, it's easy to see that an aircraft designed to carry 6 170-pounders with full fuel and baggage could be well over gross if you loaded in 6 200-pound fishing companions without offloading some fuel or fishing gear. This information may be useful on the occasion that you want to offload your mother-in-law and put her on an airliner. Also, no two aircraft of the same model will have the same empty weight or useful load. However, all aircraft of the same model will retain the same maximum takeoff weight. The reason is each aircraft begins a customizing process as soon as it's delivered to its first owner. Each addition or subtraction of equipment, each modification, requires that a mechanic revise the weight and balance records of that particular aircraft. Failure to comply with this requirement just once will throw off all the subsequent weight and balance revisions with perhaps tragic results at some point in the future. Because an aircraft is controlled aerodynamically in flight, we'll take a few minutes to review some of the basic principles of flight. The stability of your aircraft is most affected by the way you balance it. In a general sense, an airplane which is stable will tend to return to its normal attitude unaided after it has been nudged from that attitude by some external force. For example, if you're cruising in straight and level, relatively calm air, a small upgust causes the nose of the plane to pitch up, and a few more pitch oscillations of diminishing intensity will occur until you are once again riding in smooth, level flight. Your aircraft is designed so it has stability in all three axes: roll, pitch, and yaw. When you first look at the diagram of the four forces acting on an aircraft in flight, the diagram probably showed them with lift and weight opposite each other and thrust and drag in opposition. In practice, this is not exactly so, if we discount the download from the horizontal tail surface. Most aircraft are designed so that the center of gravity is actually ahead of the center of pressure, sometimes called the center of lift. The line of thrust is also usually slightly above the line of drag along the longitudinal axis. The offsetting of the forces creates a situation where the aircraft has a natural tendency to pitch nose down under certain flight conditions. To counter this nose-down tendency, the horizontal tail is set at an angle of incidence which will produce negative lift, a down force. In level cruise flight, at maximum gross weight, your plane should be flying with little or no trim because the horizontal stabilizer is producing just enough negative lift to counter the nose-down tendency of the two offsetting forces. When an upgust shoves the nose up, the angle of attack of the stabilizer lessens and may even go from negative to positive. This causes a reduction in the negative lift of the stabilizer. At this point, the center of gravity ahead of the aerodynamic center will cause the nose to pitch down. After a few seconds of down pitch, the horizontal stabilizer will regain enough negative lift to push the tail down and the nose back up. The pitching oscillations will each diminish in intensity until the tail is once again in balance with the center of gravity. An aircraft which can do this is said to have both static and dynamic stability. Now, let us suppose that in loading your plane with fuel, passengers, and baggage, you have moved the center of gravity beyond the forward limit. The horizontal tail is probably in a fixed angle of incidence and therefore will always produce the same negative lift at maximum gross and level cruise. Since you have moved the center of gravity ahead of the center of lift, you must do something to counter the additional down force of the nose. You do this by using some up elevator. As the center of gravity is moved further forward, you will at some point reach full up elevator in attempting to control the down pitching nose. Beyond that point, no additional aerodynamic control is available, and your plane will continue to dive until it hits the ground. Now, in order to assure you of full aerodynamic pitch control at all airspeeds, the forward center of gravity will be placed at a point which will assure sufficient elevator deflection at minimum airspeeds. Let's change the situation to a takeoff. The maximum downforce from the stabilizer with full elevator deflection is low because the velocity of the relative wind is low. It is possible that the airspeed attained during takeoff will not develop enough aerodynamic pressure with full up elevator to get the nose wheel off in the span of, say, the typical general aviation airport. Landing with an extreme forward center of gravity could cause a loss of control at a critical time. With relative wind slowing and ground effect diminishing the effectiveness of the stabilizer and elevator, you could just simply nose down into the runway out of control. The manufacturer of your aircraft determined the forward center of gravity primarily on the basis of adequate elevator effectiveness at slow flight speeds. Keeping the CG behind the forward limit will guarantee you of up elevator effectiveness. Now, the rear center of gravity limit is based on another concept related to positive stability, meaning the tendency for your plane to return to its trimmed attitude. Your plane has positive stability when it returns unaided to its original attitude. It has neutral stability when it does not return to trim flight but keeps going in the direction to which it was deflected. If the nose is bumped up, the plane will keep going until it stalls. If bumped down, it will dive until it hits the ground. You will be able to control situations of neutral stability. However, a plane with neutral stability will not handle as easily as the one you're accustomed to. In order to get the same thing done, you will have to exert more control force and as a result have a tendency to over-control the plane. How do you keep your plane from becoming neutrally stable? Always make sure that your center of gravity is ahead of the aft limit. Is there such a thing as negative stability? There certainly is. And from the pilot's point of view, it's the worst kind. The center of gravity is behind the center of lift, and there is no tendency for the nose to pitch down. Imagine a power-off stall with the center of gravity behind the rear limit. With positive stability, your plane will pitch down due to the location of the CG. Under negative stability, the tail-heavy craft will tend to increase the pitch up and exaggerate the stall. The action will probably be followed by a spin, possibly a flat spin, from which no recovery technique will work. A few years ago, the FAA General Aviation News published a story about a pilot who lost an airplane, literally. He was flying a small, two-place, low-wing retractable over the farmlands of the Midwest. Suddenly, the engine seized and wrenched itself right from the mounts and fell to the ground. The pilot found himself in one of those hypothetical situations which just doesn't happen. The center of gravity was out of sight behind him. Fortunately, nothing else was damaged, and his airspeed was at a high cruise. He no longer had a need for a hand on the throttle, so he put both hands on the wheel and forced it forward. He had enough airspeed to make it work, and he dove the little bird to the ground at orbital velocity. His flare consisted of a slight relaxation of forward pressure on the controls. The plane bellied into a bean field at a speed greater than his normal cruise. The pilot survived. The plane survived. The engine survived. And all were reunited in about 9 months to go flying once again. This is one of only a few recorded examples of a successful landing with the CG displaced so far to the rear. Most of the time, the results of a tail-heavy loading just leave a mess for someone on the ground to clean up. Negative stability is the worst possible condition you can deliberately place on your plane. Your aircraft is designed to fly with positive stability. You can assure yourself of it staying that way by observing the limits when loading. Now, let's review the consequences of loading an aircraft beyond the limits of the center of gravity envelope. A center of gravity ahead of the limits will, 1, produce excessive stability requiring increased control wheel forces. 2, it will also increase stalling speeds. And 3, decrease performance. A center of gravity too far aft may, 1, reduce control wheel forces with the potential for pilot over-controlling. 2, change stall characteristics from benign to violent. And 3, develop a tendency for a normal spin to become a flat spin. Most concern for balance is centered on controlling pitch along the longitudinal axis. Yaw along the lateral axis also must possess stability, but since loading only affects it indirectly, we will not discuss it further in this presentation. Roll along the vertical axis must also have positive stability. Since most planes have wing tanks and some have nacelle baggage compartments, we'll take a brief look at loading the wings. Most of the optional loading of wings occurs close to the fuselage. It is doubtful that unbalanced loads there will cause much more than a heavy wing which must be held up either with trim or muscle power. Tip tanks add another dimension. If you fly a plane with tip tanks, fuel management is a necessity. As with elevators, aileron deflection must be limited by design. Full deflection at slow airspeeds may not give you the adequate roll control when tip tank weights are grossly disproportionate. Most aircraft have only one center of gravity envelope developed for them. It is for the longitudinal plane or pitch control. The forward limit is set by the elevator effectiveness at slow airspeeds, while the aft limit is determined so that the aircraft will always have positive stability. In most general aviation aircraft, this envelope is measured in just a few inches of lateral distance. Understanding how to determine the center of gravity for a particular loading situation requires us to review a few terms. The datum is an imaginary vertical plane or line established by the manufacturer from which all measurements of arm or distance are taken. The permissible center of gravity range is measured from the datum in inches. An arm is the horizontal distance in inches from the reference datum to the center of gravity of a particular item. The mathematical sign plus is used for arms located after the datum. A minus sign is used for an item which is placed forward of the datum. Moment is the product of the weight in pounds of an item multiplied by its arm in inches. Moments are expressed in pound inches. Total moment is the weight of the aircraft multiplied by the distance between the datum and the center of gravity. The fuel load is the expendable part of the aircraft load. It includes only usable fuel, not fuel required to fill the lines or that which remains trapped in the tank sumps. Gasoline weighs 6 pounds per gallon. Kerosene weighs 6.7 pounds per gallon, and lubricating oil weighs 7.5 pounds per gallon. A station is a location in the aircraft which is identified by a number designating its distance in inches from the datum. The datum is therefore identified as Station 0. The station and arm are usually identical. An item located at station plus 50 would have an arm of 50 inches. The term percent of mean aerodynamic chord, long phrase, is used by some manufacturers to show the limits of the center of gravity. Mean aerodynamic chord is a hypothetical chord line running parallel to the longitudinal axis and is located through the geographical center of the wing. Aircraft manufacturers use several kinds of graphs and charts from which the weight and balance of their aircraft may be calculated. They are all based on what is referred to as the computational method. We will help you with the traditional graphs and tables only in this presentation.
The tables and the graphs furnished by Beach in your operating handbook provide the material you need to construct a loading schedule master. This will create a pictorial representation of the load condition for a flight and enable one to modify it as necessary. The moment limits versus weight graph, plus the occupant, fuel, and baggage tables will be taken from this handbook. Now, to begin, you will need the form for your airplane that will provide the empty weight and correct moment. When building the master for your specific airplane, information will come from its handbook. Operating the master requires a clear plastic straight edge and a pen with erasable ink. To provide ease of use and reduce the possibility of error, take the graph to a print shop and have the best enlargement to 8.5 by 11 inches that's possible. This will become your master, built on the same method that we're showing. You may want to use a loose-leaf notebook and plastic sheet protectors to contain other enlarged performance graphs for ease of use in pre-flight analysis. We find this size makes use of the master faster, and all charts will be more readable. This project is not difficult, but it does require a step-by-step understanding. As the tables and graphs that we're using in the demonstration guide appear, using the pause button on the VCR properly to evaluate each step of the lesson will be useful. This is the master that we are completing in this program. The right side of the graph displays a rising scale of weights, and a series of diagonal lines rising with moment increase is tabulated on the left side. The shaded area defines the center of gravity limits, and the scale across the bottom portrays the center of gravity limits in inches after the datum line. The construction principle is simple. At any given station, an increase in weight produces a corresponding increase in moment. A point picked off a straight line connecting two proven points at any weight within the allowed limits for the station will have the correct moment. Reference lines, once created for each station, will have a slope on the graph peculiar to that station. A line for another station may anchor on a loaded station and follow its slope parallel to the reference line until the load for the new station is reached. And then using that location as the new anchor point, another line may be attached, and this process may be repeated until all the necessary stations are loaded. Any consideration of weight and balance must begin with the empty weight and the effective center of gravity at that point. Any change in empty weight will require building another graph. Now, we have chosen to use the numbers displayed in the sample loading form in the handbook. The permanent records for your airplane will have this information, and the 337 forms will keep it current. Our hypothetical airplane has an empty weight of 2,231 pounds, with a moment of 1,712. Turning to the graph, we read up the right side scale to 2,200 pounds and interpolate for 2,231 between the horizontal lines of 2,200 and 2,300 pounds. Using the straight edge, a parallel line now may be constructed across the chart. Reading up the left side to the 1700 diagonal moment line, an origination point of 1712 will be established to start the diagonal line parallel to 1700. When two straight lines, originating at each selected value, are laid down parallel to the formatted lines, the intersection will provide the point where a given weight meets the correct moment, and this point should be marked. In actual practice, one can find these points simply by using a straight edge and visualizing the point by paying close attention to the parallel diagonal line without drawing a line. For the sake of clarity in this demonstration, we will display the intersection lines being drawn as they are drawn. When they are removed, the intersection point marks the condition of the empty weight. Using the occupant table, we will load the pilot and co-pilot station, followed by the passenger stations for a club seating configuration. The general aviation standard of 170 pounds for each occupant, except those in the front station, will be the target loading. In the interest of a possible forward loading requirement, a reference line on the forward seat station for 400 pounds is advisable. When the pilot at 170 pounds and navigational gear at 30 pounds is loaded and the intersection point is found, it establishes the basic operating weight. And since the pilot and gear must be on board before flight, all future loading on the model will require this weight. The occupant table for 200 pounds in the front seat station displays a moment of 150. Reading 200 pounds up the right scale to the 2,431-pound horizontal line defines the new weight. Adding 150 to the 1712 moment of the empty weight provides 1862 for the new moment diagonal. The intersection of these two lines is the new center of gravity, and its point should be marked. A mark for this intersection has given the 2 points needed for a straight line. Using a straight edge to draw the line and letting it rise 200 pounds above the pilot station will load the co-pilot. The 200-pound rise on the reference line will end at 2,631 pounds, found on the right side scale, and the correct moment is intersected at this point on the line without further calculation. Loading the aft-facing seats at a point 340 pounds up from the previous weight of 2,631 to the new weight of 2,971 can be done by reference to the right side scale. Turning now to the moment, a simple addition of 189 times 2 for each of the 170-pound passengers to be loaded adds 378 from the table to the moment of 2012 from the co-pilot's position, and the proper moment is now 2390. The new slope will have 1 point at the previous maximum weight at the co-pilot's position and 1 at the intersection point of the new values, and connecting these points with the straight edge will load this station, and the reference line should be drawn. Note that this has created a slope different from the forward station. Repeating this process for the club seating, the forward-facing seat station can be graphed, and it will be noted that when this is completed with seating for the occupants alone, the airplane is very close to being out of CG. The last passenger has created the problem. A fuel reference line may be plotted at any convenient location, since the straight edge will be moved from the location to build a new parallel line in almost every case. One recommendation is to anchor the fuel reference line on the co-pilot's position. This will be useful for those tanks filled to prevent condensation, or those flights where fuel might be a prime consideration. Since this line will be very close to the front seat station and has a similar slope on this airplane, the permanent display for the line should be in a contrasting color. To construct the line, start at the top of the forward station line and rise 444 pounds to 3,075 pounds, and intersect the 2345 moment, and draw a contrasting colored line. Baggage loading on the airplane may require unexpected precision. Many models have different station limits, and the pilot should be familiar with the POH to be certain that the limitations are observed. Although the Bonanza is a world leader in its class in almost every area, we have to admit that loading baggage requires a lot of planning and some creativity. The most used aft baggage position on this plane has only a 70-pound allowance. And when we lay down the reference slope for this station, it is easy to see why. There can be only 256 pounds, or a 42-gallon fuel load. The fuel load in this condition will not move the CG out of the envelope. And if the passenger weight is standard, a local flight with friends will be satisfactory. If the flight is to be a cross-country flight requiring more fuel and baggage, then attention must be given to specific weights. The actual weight per passenger might be less than standard. One may note that the safe maximum gross weight may, by virtue of environment or runway conditions, be less than that displayed on the top of the graph. When such a weight is arrived at from the charts or from pilot judgment, a visible horizontal line should be drawn in the plastic to define the weight, and this line must not be breached. The passengers for this flight have advised that there will be a 200-pound male and one tipping the scales at 194. 2 females, one weighing 160 and one weighing 120, plus an 85-pound child complete the passenger load. In addition, there will be 250 pounds of baggage. The first hard fact to be confronted is that the 250-pound baggage load is not possible. The airplane is not configured to load in the center seat section, which leaves only the aft baggage compartment and the nets back of the front seat. They have a combined total capacity of 170 pounds. 80 pounds will have to be offloaded and shipped or left behind. Having faced this problem many times, we wish the pilot luck and extend our sympathy. Drawing lines from the occupant stations will not be necessary since proximity to the reference lines permits an accurate visualization. Dots will be placed at the appropriate locations, with each weight requiring a new dot. Bonanza experience tells us that maximum possible forward loading is generally necessary when the airplane starts to approach all-up weight. To make this point, we will load the child in the front seat and the heavy men in the forward-facing rear seats. Adding 85 pounds to the front seats plus 280 to the aft-facing seats and 394 pounds to the forward-facing club seats loads the passengers, and the addition of 70 pounds of luggage in the aft position and another 100 pounds in the forward nets puts the CG out of limits for takeoff. The best seating is 200 pounds in the co-pilot position, 160 and 194 in the aft-facing seats, and 120 and 85 pounds in the forward-facing club seats. Creating a schedule for this load is a simple matter of anchoring on the top of the forward seat station, the co-pilot's position, that allows for a 200-pound person, and rising 354 pounds on the center seat station for the next heaviest people. Rising an additional 205 pounds on a line parallel to our aft seating line completes the passenger load well within CG limits. We complete our display by loading the baggage exactly as we have done before. The CG is now legal at a zero fuel weight of 3,360 pounds. Sliding the straight edge over parallel to the fuel line to anchor on the zero fuel weight position has made it apparent that a fuel load will not trespass on CG limits. Reading up the right side scale from the zero fuel weight reveals that a load of 250 pounds of fuel will be legal. Adding 12 pounds for start and taxi to the 250 pounds usable will permit a safe departure from the ramp with 43 or 44 gallons. With this pictorial representation in mind, most flights will not be referred to a loading schedule, but in any departure from a standard load, one should take the few seconds necessary to be certain that the operation will be safe. The accuracy of these graphs is largely dependent on the care in their construction and their use. The 8.5 by 11-inch enlargement should contain as much of the actual graph as possible. If a solution on the graph lies in a borderline area, it would be wise to run it again to check for possible errors. Loading of the different models varies depending on center of gravity limitations and performance under different conditions. Although the layout looks different on this sample V35B model, the principles are the same. This model offers several possibilities for improper loading, and one must use the proper graph to create the master. One may note on this sample that 2 heavy people in the front seats and full fuel may move the CG too far forward, which will require some weight in the center seats or the aft baggage. With 4 standard weight people on board, the baggage loading will require planning if more than 50 or 60 pounds is needed. The Bonanza fuel system requires careful monitoring to be certain of the total fuel on board. Many accidents attest to the failure to follow this procedure. An envelope for the B-36TC also looks different because of the additional weight and the accommodations required for the turbocharger installation. Proper weight and balance is particularly important on this model. The takeoff and landing weight should be considered for every flight. It is a direct reflection of structural integrity. Although many Bonanza flights are conducted each and every day without reference to proper loading, the FAA considers it important enough to require a permanent schedule for revenue flights. The sample graph for the B-36TC, with the fuel reference line anchored on the co-pilot's position, shows that front seat loading must be handled carefully, or weight must be loaded in aft seats. Although 6 seats filled keeps CG in range, it appears that only about 70 pounds of baggage may be loaded at 0 fuel weight, and the weight portion of the graph suggests that only about 45 gallons of fuel will be available. And with this loading, the airplane is dangerously close to being out of CG. In case of an accident, investigators determine quickly if the envelope has been breached, and insurance companies may be happy to make the owner very unhappy at settlement time. In normal operations, a pilot will encounter many situations that will require more than just an eyeball analysis to ensure proper loading. 60 seconds with a scheduling master may be time well spent. When a pilot becomes familiar with the schedule, entering the anchor dots in erasable ink on a plastic sheet will be done very quickly, and the straight edge will lead to the center of gravity. Management of weight in the Bonanza is a very important ingredient in safety of flight. Here, we have explored weight as a factor in balance, leading to stability and control. In later tapes, we will consider the relationship of weight to performance, and we hope these very functional tools will help to increase safety in your operation.
Well, this presentation on weight and balance has taken us through some of the following concepts: aircraft stability, center of gravity envelope, the hazards of loading an aircraft either too far forward or too far aft, reasons for the center of gravity limits. We also reviewed the following terms: datum, arm, moment, empty weight, maximum takeoff weight, maximum gross weight, useful load, maximum ramp or taxi weight, center of gravity, fuel load, moment index. The total fore and aft movement of the center of gravity for most general aviation aircraft is limited to a few inches. For example, a Beechcraft Baron A55 allows for 14 inches between fore and aft limits when the aircraft is light, but only 6.6 inches when it is at maximum gross. It should be clear from this discussion that careless loading of any aircraft, from an ultralight to a 747, can create problems for the pilot from which there may be little or no chance to recover. Large numbers of flights are conducted each day with 1 or 2 persons on board and only a briefcase and a map case for baggage. The need to calculate weight and balance is remote in these situations, especially when the atmosphere is near standard. However, when the loading of your aircraft involves weight at each station, bulky baggage, cargo, or a gross weight approaching maximum allowable, take the extra few minutes necessary to calculate your weight and balance. It's not only safer, but proper arrangement of weight could save you a few dollars in fuel costs and may get you to your destination a little sooner. We hope that this airmanship presentation will bring you greater safety and more pleasure to you as you fly. My name is Jack Wellman. I'm Director of Program Development for Airmanship Incorporated, the knowledge center for today's pilots.